Hello everyone. In previous lecture, we have studied the different types of ions and peaks under mass spectrometry. Now, in today's lecture, I am going to discuss about fragmentation pattern. For the study of fragmentation pattern in a different classes of organic compounds, it is necessary to understand the rules of fragmentation. So, let's begin with rules of fragmentation and also we will study the fragmentation pattern. So what is fragmentation? The fragmentation process, it is nothing but the cleavage of bonds. That means bond breaking. So the bombardment of molecules by an electron beam with energy between 10 to 15 electron volt usually results in the ionization of molecules by removal of one electron, and that leads to the formation of molecular ion. When the energy of electron beam is increased between 50 to 70 electron volt, these molecular ions acquire a high excitation, resulting in their breakdown into various fragments. This process is called as fragmentation process. As I have explained in previous lecture, the molecular ion or parent ion is formed by the loss of single electron at lowest ionization potential from a molecule. That means whenever the bombardment of molecule occurs by an electron beam with energy between 10 to 15 electron volt, usually that results into the ionization of molecule by removal of one electron, and there is the formation of molecular ion as well as called as a parent ion. When the energy of electron beam is increased between 50 to 70 electron volt, these molecular ions acquire a higher excitation. As we have discussed that the molecular ion is unstable, and due to the instability of molecular ion, that will be further fragmented into daughter ions or called as a fragment ions. And this process, that is the cleavage of the fragments or formation of number of fragments, this process is called as a fragmentation process. The molecular ion, radical ion, that will be converted into number of fragments like M1 plus and M2. That means due to the instability of molecular ion, that will be further fragmented into daughter ions or fragmented ions. So this process is called as a fragmentation process. Now what are the general rules for fragmentation? The relative height of the molecular ion peak is greatest for the straight chain compound and decreases as the degree of branching increases. So for the study of fragmentation pattern in a different classes of organic compound, it is necessary to understand the rules of fragmentation. Here, when we observe the straight chain compound as well as the branch chain compounds, there will be the variation in the molecular ion peak. So, the relative height of the molecular ion peak is greatest for the straight chain compound, and it decreases as the degree of branching increases. Because in case of branch compounds, the cleavage it occurs at the branching point, and due to the cleavage of branching point, there is the formation of a stable carbocation, and hence the relative height of the molecular ion peak is greatest for the straight chain compound as compared to the branch chain compound. As we know, the fragmentation is nothing but the cleavage of the bonds. So, in the fragmentation process, there is a cleavage of carbon-carbon single bond, carbon-hydrogen bond, or carbon-nitrogen bond. So, if you observe, the compounds with the same class has a unique fragmentation pattern used as fingerprint for qualitative identification. Suppose we consider the straight chain alkane and the branch chain alkane. In case of branch compound, the cleavage occurs at branching point, and due to the cleavage at the branching point, there is a formation of a stable carbocation as a molecular ion of branch chain alkane is converted to stable carbocation very fast. Therefore, the molecular ion in case of branch chain alkane, it is very less stable, and depending upon the stability of molecular ion in the branch chain alkane, the intensity of the molecular ion is less as compared to straight chain alkane. So, the relative height of the molecular ion peak is greatest for the straight chain compound, whereas it will be less in the branch chain compound as it decreases depending upon the degree of branching increases. Second rule, the relative height of the molecular ion peak usually decreases with increasing molecular weight in a homologous series. We know that in the homologous series, each member differ by 14 mass units. So, in the alkane, there will be the difference in that next member by a 14 mass unit or by CH2 group. So, the relative height of molecular ion peak usually decreases with increasing molecular weight in a homologous series. Third rule, the cleavage is favored at alkyl substituted carbon atoms. The more substituted, the more likely is cleavage. This is consequence of the increased stability of a tertiary carbon atom over a secondary, which in turn is more stable than a primary carbocation. As now I have explained that the cleavage occurs at the branching point, or it also occurs at alkyl substituted carbon. Whenever the cleavage it occurs at alkyl substituted carbon atom, then there is a formation of a carbocation which is more stable. So if we consider the stability of the carbocations, here the tertiary carbocation is more stable than secondary, than primary, than that of methyl carbocation. So it is the order of stability of the carbocations, and it is only due to that position of the carbon atom and the alkyl group, or also the cleavage it occurs at the branching point. So cleavage it is favored at alkyl substituted carbon atom, and that leads to the formation of more stable carbocation. First of all, the molecular ion is formed by the bombardment of energetic electron. Then the molecular ion undergo fragmentation process in which free radicals or neutral molecules are lost from the molecular ion. The general tendency for fragmentation is to give the most stable fragments as possible. So the radicals are inherently more stable than the carbocations since these are less electron deficient. However, these are stabilized by some factors which stabilizes the carbocations. If we consider the number of factors stabilizing carbocations, that may be plus R inductive effect or plus R in resonance effect, like that. Resonance effect, inductive effect stabilizes the carbocations. Here, the number of alkyl group increases, also increases the stability of carbocation. So, the positive charge present on such a carbon having number of more alkyl groups. So, the tertiary carbocation is more stable as compared to methyl, as compared to primary or secondary carbocation. Now, the next important rule involved in fragmentation process is Stevenson rule. So what is the Stevenson's rule? Here, when an ion fragments, the positive charge will remain on the fragment of lowest ionization potential. Generally, the largest substituent at a branch is eliminated most readily as a radical, presumably because a long chain radical can achieve some stability by delocalization of the lone electron. The Stevenson rule is very important rule in the fragmentation of mass spectrometer. So, as we know, the fragmentation process it occurs through either by homolytic or heterolytic cleavage, but there is a cleavage of the bond, and if the fragmentation occurs, then we get radical and cation. So according to Stevenson rule, the fragmentation occurs in such a way that positive charge resides on a fragment with low ionization potential. That means generally the positive charge it presents on a small fragment. That is, the smaller fragment acquires a positive charge and a larger fragment acquire a radical. So there is a formation of a radical and a positive charge. So according to the Stevenson rule, the fragmentation occurs in such a way that positive charge will remain on the fragment of lowest ionization potential, generally on small fragments, and larger fragment will acquire a radical. So if we take the example here, the cleavage of 1-methyl pentane. So this will be the structure of 1-methyl pentane. So here will be the fragmentation and we get the fragment. So one is the largest fragment. Here in that largest fragment there is a presence of radical on the carbon, and this will be the smaller fragment which acquire a positive charge. So the fragmentation occurs in such a way that positive charge resides on a fragment with low ionization potential, generally on small fragments, and larger fragment acquires a radical. So on the more high substituted fragments, that is the one with lower ionization potential, the fragmentation in that positive charge will be present. In this fragmentation, 1-methyl pentane, the positive charge remains on the more high substituted fragment, that is the one with lower ionization potential. So this one is the Stevenson rule. Now the next one, double bonds, cyclic structures and especially aromatic or heteroaromatic rings stabilize the molecular ion and thus increases the probability of its appearance. If we consider the alkenes or the number of cyclic structures, especially the cyclic structure, aromatic or heteroaromatic rings that will stabilize the molecular ion and also increases the probability of its appearance. Now the next one. Double bonds favor the allylic cleavage and it will give the resonance stabilized allylic carbonium. So if we consider the example 1-butene having the carbon-carbon double bond. So in this example, the cleavage occurs at this carbon atom. Cleavage occurs at this carbon atom and we'll get the formation of CH2 double bond CH, CH2 plus. So here the removal of this CH3 group, and due to that there is the formation of such a fragment. So double bond it will favor the allylic cleavage and it will give the resonance stabilized allylic carbonium ion. So this will be the resonance stabilized carbocation of the allylic compound. This 1-butene is a terminal alkene, and if we consider the characteristic of the 1-butene, here the peak observed for 1-butene is M by Z at M by Z 41. M by Z 41. So this will be the characteristic peak observed in the 1-butene due to the cleavage at allylic carbon. So here the 1-butene is the terminal alkene, and for the terminal alkene the characteristic peak can be observed at M by Z 41. If we consider the second type of the cleavage in 1-butene, the vinylic cleavage, it also occurs through homolytic cleavage, but the vinylic ion or the cation which is formed, it is less stable as compared to allylic carbocation. So here the terminal carbon-carbon single bond, it undergo the cleavage and there is the formation of such a type of the allylic carbocation, and this allylic carbocation is more stable as compared to vinylic carbocation in the same structure of 1-butene. So first of all, ionization occurs, there is the formation of a molecular ion, and this molecular ion will further undergo the fragmentation by homolytic cleavage, either by vinylic or either by allylic carbon-carbon cleavage. So here the allylic cation formation which occurs, it is more stable as compared to vinylic cation. So we should remember that both that double bonds which are present, that will be helpful for the formation of the more stable cation. So double bonds favor the allylic cleavage and it will give the resonance stabilized allylic carbocation. Now why this allylic carbocation is more stable? Only due to the resonance stabilization. Due to the resonance stabilization, it is more stable as compared to that of the vinylic carbocation. Now next rule, that is nothing but about saturated rings. The saturated rings tend to lose the alkyl side chain at the alpha carbon atom. This positive charge tends to stay with the ring fragment. So if we take this example here, the saturated ring tend to lose the alkyl side chain at the alpha carbon atom, and here also the positive charge tends to stay with the ring fragment. So we should remember that here the mass spectrum of N-propyl cyclohexane, there will be the alkyl side chain and also the ring, saturated ring. So if we consider the fragmentation of such a compound, here the alkyl side chain, on that the radical is present, and on the saturated ring we have to represent the positive charge. So the positive charge tends to stay with the ring fragment. Further, this ring fragment undergo the fragmentation and that will leads to the formation of a new fragment. So there here will be the fragment form having m by z is equal to 55. So the cleavage of this ring, saturated ring occurs, and there, again there is a formation of a new fragment. So it is also important one. Saturated rings tends to lose alkyl side chain at the alpha carbon atom. This positive charge tends to stay with the ring fragment. Next one. In alkyl substituted aromatic compounds, the cleavage is very probable at the bond beta to the ring, giving the resonance stabilized benzyl ion, or more likely that will be the formation of tropylium ion. So we have to take this example, mass spectra of N-butyl benzene. Here in the N-butyl benzene, the cleavage, it occurs at this beta bond, which is beta to the ring. So it is the alpha position, this will be the beta. So the cleavage at this beta position occurs and that will leads to the formation of this fragment. Further, this fragment undergo the resonance stabilization, and due to the resonance stabilization there is a formation of tropylium ion. Also there is a formation of a benzyl ion, more likely the formation of a tropylium ion, and due to the formation of tropylium ion we get the peak at m by z at 91. So that is also important thing. If the alkyl substitute present at the aromatic compound, then the cleavage occurs at beta position to the ring. So bond which is present beta to the ring, so cleavage occurs at the beta bond, and that will give rise to the formation of a ion, benzyl ion, and further undergo the resonance stabilization or the rearrangement occurs that leads to the formation of a tropylium ion. And due to the formation of tropylium ion, we get the peak at M by Z91. So this will be the Mac-Lafferty rearrangement ion, and due to the formation of such a ion, also peak is observed at M by Z92. So we have to study in detail about the Mac-Lafferty rearrangement in next lectures. Okay, so this will be the important for alkyl substituted aromatic compounds. Now the next one, the cleavage is often associated with elimination of small, stable, neutral molecules such as carbon monoxide, olefins, water, ammonia, hydrogen sulfide, hydrogen cyanide, mercaptans, ketone, or alcohols, often with rearrangement. So in different organic compounds, there is also the cleavage which is associated with the elimination of a neutral molecules which are stable molecules. For example, carbon monoxide, CO, olefins, also the water, H2O, ammonia, NH3, H2S, hydrogen sulfide, hydrogen cyanide, HCN, ketone functional group, or the number of alcoholic functional groups that will be removed simply by rearrangement. So the cleavage is associated with the elimination of small, stable, neutral molecules. Now there are the different factors which influence the fragmentation process. First important factor is bombardment energies. So how much amount of energy is used for bombardment, and that will lead to the formation of a molecular ion. Depending upon that also the fragmentation, it shows the variation. Second important factor, that is functional group. Which functional group is present? On that basis, the fragmentation or the cleavage of the bond occurs. The third important factor, that is thermal decomposition. So on that basis also the fragmentation is variable. So these are the three important factors influencing fragmentation process: bombardment energies, functional groups, thermal decomposition. Now we have studied the different rules for fragmentation. So it will be only the summary or the different points which we have to remember for the fragmentation in mass spectrometry. So first important rule is that compounds with the same class has unique fragmentation pattern used as fingerprint for qualitative identification. Then, as we have studied, fragmentation is nothing but the cleavage of bonds. So in the fragmentation process, there is a cleavage of carbon-carbon single bond, carbon-hydrogen, carbon-nitrogen bond occurs. Hence, it is necessary to understand the rules of fragmentation for different organic compounds. So first important rule, the cleavage occurs at alkyl substituted carbon or at the branching point to give the most stable carbocation. So here when we take the example, the cleavage occurs at this carbon atom, and in this case the cleavage occurs at this carbon atom. Already I have explained that the tertiary carbocation is more stable as compared to secondary carbocation, as compared to primary or as methyl carbocation. And the general tendency for fragmentation is to give the most stable fragments as possible. So here the fragmentation occurs, and due to the fragmentation at alkyl substituted carbon, there is the formation of most stable carbocation. Second rule, if there is the double bond or the allylic cation or the arenes are present, that type of the fragmentation that will resist in such a examples. So in the double bonds in arenes or in allylic cations, there is a resistance of fragmentation. Then the next one, even electron rule. So what is even electron rule? Even electron spaces will not fragment into two odd electron spaces, but fragments into cation and neutral molecule. So it is called as even electron rule. So such a species, even electron species, will not fragment into two odd electron species, but that will be fragmented into cation and neutral molecule. Next important rule, frequently neutral fragments such as CO, C2H2, H2O, NH3, H2S are lost. So during the cleavage or during the fragmentation process, there is the elimination of more stable or neutral groups like CO, C2H2, H2O, NH3, H2S, HCl, etc. that will be lost. So that is also important rule. Next one, Stevenson rule. So according to Stevenson rule, fragmentation occurs in such a way that the positive charge resides on fragment with low ionization potential, generally on small fragments. So the positive charge is present on the small fragment and the radical will be acquired by the larger fragment. Then the next important rule, that is the nitrogen rule. So what is nitrogen rule? Compounds with even number of nitrogen or lacking nitrogen, it gives the molecular ion peak at even m by z value and vice versa. Or compound with odd number of nitrogen give the molecular ion peak at odd m by z value. So this can be explained by taking this example. So here if we consider the compound like ethene, this will be the methylamine, and the third example is phenylhydrazine. So in this case, in ethene there is no nitrogen, so the peak or the molecular ion peak is observed at m by z 26. For methylamine, the peak is observed at 31, and for phenylhydrazine, the peak will be observed at 108. So if we consider here in ethene, there is no nitrogen. In the methylamine, only one nitrogen. And in phenylhydrazine, there is a presence of two nitrogens. So when we look at m by z values, then we get here for ethene the molecular ion having m by z value 26, which lacks the nitrogen. So the compounds with even number or that of the lack of nitrogen give the molecular ion peak at even m by z value. But if we consider here the methylamine, there is the presence of only one nitrogen, that means having the odd electron. So the m by z value is also odd. Then phenylhydrazine having the two nitrogens. So as the compound with even number of nitrogen gives the molecular ion peak at even m by z value. So that will be the important example, and also we can say this will the nitrogen rule to assign the molecular weight of the different organic compounds. So compounds with even number of nitrogen or lacking nitrogen gives the molecular ion peak at even m by z value, and if the compound having the odd number of nitrogen, that will show the molecular ion peak at odd m by z value. Now let us see the general modes of fragmentation. So the fragmentation of the molecular ion, it takes place in the following modes. First important one, that is simple cleavage. Simple cleavage also occurs by homolytic cleavage, by heterolytic cleavage, or also by retro-Diels-Alder reaction. In some cases, there may be the rearrangement. The rearrangement reactions which are accompanied by transfer of atoms, that may be by scrambling, by McLafferty rearrangement, and also by elimination. So let us see the fragmentation by different terms. First of all, by homolytic cleavage. Homolytic cleavage is also known as alpha cleavage. So it is one of the simple cleavage. Homolytic cleavage, it is initiated by the radical site. Here, the odd electron ions have an unpaired electron which is having the tendency to create new bond. If any new bond is formed, then the energy will be released and that energy will be used for the cleavage of other bond. So that is the homolytic cleavage, and homolytic cleavage is also known as alpha cleavage. So if we take this example, here RCH2 CH2R, homolytic cleavage, it occurs at this point. Here the cleavage or the rupture of the bond, it occurs at the this bond, carbon carbon single bond, and due to the cleavage of this carbon carbon single bond, we get this formation of a new fragment. So here the odd electron ions have an unpaired electron which is having the tendency to create a new bond. If any new bond is formed, then the energy will be released and that energy will be used for the cleavage of other bond. So if we consider there is a formation of such a type of the bond, such a type of the fragments RCH2 plus and RCH2. So symmetrical cleavage, it is also known as a symmetrical cleavage. Here the fragmentation is due to the electron redistribution between the bonds, carbon-carbon single bonds. So homolytic cleavage is also known as alpha cleavage and it is initiated by the radical site. Now the next one, heterolytic cleavage. So here the fragmentation by movement of two electrons occurs. In this type of cleavage, both the electrons of the bond are taken over by one of the atoms. The fragments are an even electron cation and a radical with the positive charge residing on the alkyl group. It is designated by a conventional arrow. So such a type of the arrows can be used to represent the heterolytic cleavage to the alkyl group. It is designated by a conventional arrow like that. So to signify the transfer of a pair of electrons in the direction of the charge side, such type of the arrows can be used. So in heterolytic cleavage, the cleavage of CX bond take place, which is more difficult than carbon-carbon single bond. If you consider X, that will be the heteroatom like nitrogen, oxygen, sulfur, chlorine, etc. So the positive charge is carried by the carbon atom instead of the heteroatom. So if we consider here, the positive charge is carried by the carbon atom instead of this heteroatom oxygen. So a heterolytic cleavage, in that the cleavage of CX bond occurs and it is more difficult as compared to carbon-carbon single bond. So in this type of the cleavage, both the electrons of the bond are taken over by one of the atoms. The fragments are an even electron cation and a radical with the positive charge residing on the alkyl group. So here the positive charge present on the alkyl group. So if we consider the conventional arrows, we can represent here the cleavage of this type of the compound. This will be the ether and the cleavage occurs at this position, and due to the cleavage we get the formation of these fragments. So it is the heterolytic cleavage. This will be the second example, C4H9Br molecular ion. Here also the cleavage occurs in between CBr bond. So cleavage of CX bond, that means CBr bond. The X that may be heteroatom like NOS, Cl, Br, etc. So that like that the cleavage occurs at CX bond, which is more difficult as compared to carbon-carbon single bond. So we get the formation of one fragment as a Br radical and the other, that is the cation, C4H9 plus cation, butyl cation. So that is the heterolytic cleavage. Third one, retro-Diels-Alder reaction. Here, the elimination by multiple sigma bond rupture occurs. So, cyclohexene is broken down to diene and dienophile, and it can be explained by one or two electron mechanism. So, if we take the example of retro-Diels-Alder reaction, here the cyclohexene is broken down into two intermediates. One is the diene and the second one is the dienophile. And it can be explained by one or two electron mechanism. Let us see. First of all, one electron mechanism. So cyclohexene undergo the one electron mechanism for the cleavage, formation of first of all molecular ion, ionization of cyclohexene forms the molecular ion. Further, molecular ions will be fragmented into the formation of these two fragments. If we consider the second mechanism, two electron mechanism, again the cyclohexene undergo the ionization to form molecular ion, and after the formation of a molecular ion, further undergo the fragmentation to form these two fragments. So that is the retro-Diels-Alder reaction. Example is cyclohexene by one electron mechanism and also by two electron mechanism, formation of new fragments. Now the next one, rearrangement reactions accompanied by transfer of atoms. So first of them, that is scrambling. Here the fragmentation giving rise to stable carbocation. In certain cases, fragmentation takes place at bond which gives stable carbocation. For example, molecular ion from the alkyl benzene undergoes the fragmentation at the benzylic bond and final product is 7-membered cyclic ion, which is also known as a tropylium ion. So first of all, the formation of a cation, and again further by the transfer of a atom that will leads to the formation of a new carbocation, which is a 7-membered cyclic ion, tropylium ion, which is more stable. So in certain cases the fragmentation takes place at bond which gives the stable carbocation. So here the formation of a stable carbocation, tropylium ion. First of all, fragmentation occurs at this carbon atom and removal of this R alkyl group, formation of a benzyl ion, and further the transfer of the carbocation will get the formation of a tropylium ion which is more stable. So the rearrangement leads to the formation of a tropylium ion which is more stable ion. Peak is also observed at M by Z, tropylium ion having M by Z 91, and here M by Z peak value observed at M by Z 92. So this will be the first scrambling. Second one, McLafferty rearrangement. So what is a McLafferty rearrangement? The fragmentation due to rearrangement of molecular or parent ion. Here, the cleavage of bonds in molecular ion, it occurs due to the intramolecular atomic rearrangement. So, McLafferty rearrangement, it is nothing but one of the intramolecular atomic rearrangement where the cleavage of the bond in molecular ion occurs. And that leads to the fragmentation whose origin cannot be described by simple cleavage of bonds. When fragments are accompanied by bond formation as well as a bond for breaking, a rearrangement process is said to have occurred. Such a rearrangement involves the transfer of a hydrogen from one part of the molecular ion to another, via preferably a formation of a 6-membered cyclic transition state, and this process is favored energetically because as many bonds are formed as are broken. So the compounds having hydrogen atom at position gamma to carbonyl group have been found to a relative intense peak, and this is probably due to rearrangement as well as due to the fragmentation. So here the fragmentation is accompanied by the loss of neutral molecule. This rearrangement is known as McLafferty rearrangement. So the rearrangement results in the formation of charged enols and the formation of neutral olefins. Formation of a charged enol and formation of a neutral olefin in the McLafferty rearrangement. So here if we consider this rearrangement, the compounds containing hydrogen at position gamma to the carbonyl group, that will show the intense peak, relatively intense peak, and this is only due to the rearrangement. And here the fragmentation is accompanied by the loss of neutral molecule, and there will be the formation of neutral olefin and the enol. So if we consider this carbonyl group, molecular ion formation occurs first of all, then the position, if you observe here, alpha, beta, gamma. So the gamma hydrogen is present, and this gamma hydrogen is responsible for the rearrangement, and after that the fragmentation occurs that leads to the formation of the neutral olefin and the enol. So the fragmentation is accompanied by the loss of neutral molecule. This rearrangement results in the formation of a charged enols and the formation of a neutral olefins. So to undergo the McLafferty rearrangement, a molecule must possess an appropriately located heteroatom. First important condition to undergo the McLafferty rearrangement, it should have an appropriate located heteroatom, for example oxygen, sulfur, nitrogen, chlorine, etc. So if heteroatom is located at appropriate position, that compound will undergo the McLafferty rearrangement. Then the second important condition, a double bond. It should have double bond. Then next one, an abstractable hydrogen atom that should be present at the gamma position of the carbonyl system. So it is also the important condition of McLafferty rearrangement. A molecule must possess an abstractable hydrogen atom which should be gamma to carbonyl system. So only those molecules which possess an appropriately located heteroatom or double bond and abstractable hydrogen atom which is gamma to carbonyl system can show McLafferty rearrangement. Now it will be the table for the common McLafferty peaks in the spectra of carbonyl groups. So if you observe the compound type aldehyde, there is the substituent, and if we consider the peak observed by McLafferty rearrangement, that will be at M by Z 44 for aldehyde, for methyl ketones 58, amide 59, acid 60, ethyl ketone having at 72, and methyl esters at 74. So common McLafferty peak in the spectra of carbonyl groups. Carbonyl group from aldehyde, methyl ketone, amides, acids, ethyl ketone or methyl esters. Now the next important thing, that is elimination. By that elimination also the fragmentation occurs. One of the mode of fragmentation. Fragmentation due to loss of small molecule. The loss of small stable molecules such as H2O, CO2, CO, C2H4 from the molecular ion during fragmentation. So the neutral stable molecule will lost during the fragmentation. Elimination of H2O, CO2, CO, C2H4. For example, an alcohol readily loses H2O molecule and it shows a peak at M by Z 18 or 18 mass units less than the peak of molecular ion. So if we take this example of alcohol, here also the loss of the small stable molecule such as H2O occurs, and due to that H2O removal we get the peak M by Z 18, and formation of such a type of the another fragment. So loss of small stable molecule from molecular ion during fragmentation such as H2O, CO2 occurs. An alcohol readily loses H2O molecule and shows a peak at 18 mass units less than the peak of molecular ion. Fragmentation adjacent to the branching point. In case of branch alkanes, the bond fission it takes place adjacent to the branching point. Hence, that leads to the formation of more stable carbocation. Example, 3-methyl pentane, formation of the new fragment at M by Z 57 and also at M by Z 29. So in case of a branch alkanes, the bond fission takes place at the adjacent to the branching point. So here branching is present. So the branch point adjacent to the branch point, there is a cleavage of this carbon-carbon single bond, and due to the rupture of the carbon-carbon single bond, here is the formation of a fragment M by Z 57 and M by Z 29 in case of 3-methyl pentane. Now, the fragmentation patterns and fragmentation characteristics in relation to the parent structure and functional groups. One by one, we will see. First of all, saturated hydrocarbons. So, in straight chain compounds, there are the different types of the straight chain compounds like alkane or the different hydrocarbons. So, what are the rules for straight chain compounds, especially if you observe the mass spectra of alkanes? Here, first one, the relative height of the parent peak decreases as the molecular mass increases in the homologous series. Second important thing, the molecular ion peak is normally present, although it is weak, but it is normally present. Then the spectra generally consist of clusters of the peak separated by 14 mass units corresponding to differences of CH2 groups. The largest peak in each cluster represents CnH2n plus 1 fragment. This is accompanied by CnH2n and CnH2n minus 1 fragment corresponding to the loss of 1 and 2 hydrogen atoms respectively. So in straight chain alkanes, there is a fragmentation of each and every carbon-carbon single bond. So due to the cleavage of carbon-carbon single bond, there is the formation of number of fragments and there is a formation of cluster of peaks, and each cluster of peak is separated by 14 mass units corresponding to the differences of CH2 group. So if you observe the spectra, generally it consists of cluster of the peak only due to the cleavage of carbon-carbon single bond. So saturated straight chain alkanes, if you observe, there is the cleavage of each carbon-carbon bond, and due to this carbon-carbon single bond, there is a formation of a cluster of peaks which are observed, and these are separated by 14 mass units corresponding to the difference of CH2 groups. The relative height of the parent peak decreases as the molecular mass increases in the homologous series. And for branch chain hydrocarbons, if you observe in branch alkanes, greater will be the branching in alkanes, that less appearance will be observed for the molecular ion and intensity of the molecular ion will be low. So as compared to straight chain alkanes, in branch chain alkanes, the molecular ion peak is less intense, intensity of the molecular ion will be low, and the appearance of the molecular ion is also less. Bond cleavage takes place preferably at the site of branching. Due to such a cleavage, more stable secondary or tertiary carbonium ion formation occurs. So as I have explained, in the branch chain alkanes, the cleavage occurs at the branch point, or the bond cleavage takes place preferably at the site of branching, and that leads to the formation of stable carbocations. Next, Generally, largest substituent at a branch is eliminated readily as a radical, and the radical achieves the stability by the delocalization of lone electron. If we consider the different examples, we get that the largest substituent at a branch is eliminated readily as a radical, and it is due to only the stability can be achieved by delocalization of lone pair of electrons. Next one, greater the number of fragments results from the branch chain compound compared to the straight compounds. This is due to greater pathways available for the cleavage. So in today's lecture, we have discussed some rules of fragmentation, important rules of fragmentation like Stevenson rule, nitrogen rule, even electron rule, like that. In next lecture, we will discuss the number of fragmentation pattern with some examples and rules. Thank you.